All right, our final talk in the maintainers track before the break is about Dask DataFrame 2.0 and will be given by James Bourbeau. Let's give James a warm welcome.
Awesome. Thanks, everyone. Thanks for coming to the talk. Appreciate it. Can folks in the back, hopefully, can you hear me? We're good? Okay, great. Awesome. So, I'm excited to talk about what's basically a rewrite from the ground up for Dask DataFrame. Internally, we're sort of calling this Dask DataFrame 2.0. Dask's versioning is fun, so it's not actually 2.0. So anyways, I'm excited to talk about that, talk about some of the technical improvements that were made along the way, how that translates into performance for Dask DataFrame, and then comparison to a few different libraries in the space, in particular Spark, DuckDB, and Polars. A little bit about me, although I guess not very much. I'm James. Hey, everyone. I work on Dask. Also, longtime SciPy attendee, so it's nice to see some familiar faces in the crowd. I'm an engineer at Coiled, where we work on, among other things, deploying Dask on the cloud. Although I'm here talking to you today, in fact, I want to give a special thanks to these folks. So my colleagues Patrick, Florian, and Hendrik at Coiled, and our collaborator Rick at NVIDIA. This is the group that actually pushed forward most of, all of the efforts I'm going to talk about today, all of the technical improvements as well as the benchmarking efforts as well. So I just wanted to make sure to give them a shout out. So to kind of set the table for the talk, we're going to start talking about technical improvements, recent technical improvements, Dask DataFrame, benchmarking, and then tease a little bit what's next for Dask. So the first technical improvement had to do with how we handle string data in Dask DataFrame. So this has been around for a little bit. Actually, I think I might have given a SciPy talk last year about this, but it's on by default now, which is the important thing. So now Dask uses PyArrow-backed string data types by default. So this is important for a couple of reasons. The first is and this is actually the biggest reason, is they have a much smaller memory footprint. So historically, Dask has just inherited Pandas' default behavior, which is to use sort of vanilla Python objects for handling string data. And the PyArrow string representation is just much more compact. So it depends a little bit on the cardinality of your string data, but you'll see it's pretty common to see 2x improvements in memory usage. So this has a huge impact just because you can do the same exact computation on half the hardware, or roughly on half the roughly half the cost for the computation. So this is a really big win. The other reason is it has better performance. So the actual sort of string manipulations are faster in PyArrow. Depends on what operation you're actually doing. But one of the bigger performance impacts has to do with the GIL. So when you're just running standard Pandas code, the GIL doesn't matter that much. But whenever you transition to running things on Dask and like a multi-threaded environment, the GIL can have serious performance impacts. So PyArrow strings generally release the GIL. They're a lot more GIL friendly, so you see a big performance improvement when dealing with strings in Dask now. So that's the first technical improvement. The second one I'm going to talk about was our new shuffling algorithm, which helps. So when dealing with distributed data frames, anytime you need to do sort of a sort operation, or sort values, or you need to do a join or a merge, you end up doing this big shuffle and sorting of the data, and that's actually really expensive. So our new algorithm helps a lot there. So we have a new peer-to-peer shuffling algorithm that happens to also be based on Arrow, and it helps in a couple of different ways. The first is reducing the just complexity of a shuffling operation. So previously, the task-based shuffling was order n log n, and the new P2P shuffling algorithm is order n. So give that a sort of schematic here. So on the left-hand side, also we're not going to go into all the details here. We could talk for a couple hours about all the changes that went into the shuffling algorithm, but I do link down there to a write-up that does sort of a deep dive into the technical background for all of this. So the previous task-based shuffling is shown on the left, and the really the two main bottlenecks are the first is you see this like large intermediate layer. That's sort of where the number of tasks in the shuffling operation pretty much explode, and that can really overwhelm Dask's scheduler. And then actually if you look at the arrows after the intermediate results, how they sort of connect to the blue output partitions, that ends up being just lots of network communication in your computation, which is also going to be slow. If folks are familiar seeing these in the Dask dashboard, you'll see lots of just bright red in these shuffle operations, which is not a good sign. The P2P shuffling algorithm sort of hides a lot of that complexity away from the scheduler. So we have just this kind of single barrier task in between. So it cuts down on the complexity of the operation. It also does it in a much reduced fixed memory footprint. So previously, with the old shuffling algorithm, you actually had to store the entire distributed data set in memory at some point. So if you want to shuffle a 10 terabyte, data set, you have to have 10 terabytes of memory sitting around, which is a big ask sometimes. So yeah, now we actually by default will spill to disk in the backend, so we're able to better utilize the hardware you may have laying around. So now we can do it with a much smaller amount of memory. So the last, but definitely not least technical update I wanted to highlight was Dask added a query optimizer. So previously, Dask would just kind of more or less naively, whatever code you give us will kind of operate sequentially, and we did some optimizations, but we didn't really rewrite your statements at all. So our new query optimizer will actually perform a few optimizations that had a really big impact on performance. The first is column projection and predicate pushdown. So this is sort of a standard, any kind of query planner should come with this. This works generally for every workload. This will improve it. So what that does is there we go. So if you have code like this, so this is sort of standard DataFrame looking code. You read in a couple of data sets with read parquet, perform a merge on some column, do some, I think you can see my mouse, great. Do a merge, do some filtering, and then maybe some group by reduction, something like that. If we wrote that out schematically, we would have our read parquet calls some expensive shuffling operation from the join here. Then we would filter our data and then do our group by. And at the end of the day, we actually only care about a couple of columns. In this particular case, the customer key column and the order total column. So what our new query planner will do is actually sort of track the columns that you actually need for your operations, and then it will actually push those up through, even if they occur sort of towards the bottom of your computation. It will push those up higher to the original I/O call. So it'll only read in the columns you actually need. It'll also, to the extent possible, push that filtering into the I/O layer as well. So at the end of the day, basically all the downstream stuff still happens. It just happens on a lot smaller data, which is always a good thing. The second optimization I wanted to bring up was, so this is now more specific to Dask or really distributed data frames. Libraries like Dask and Spark is auto repartitioning. So for folks who have used Dask before, you'll be aware that how you partition up your data set can have a big impact on your computation. In particular, you want to avoid really small partitions. So if you have, 100 different partitions and they're each, 2 rows. This is a bad example. You shouldn't be using Dask in this case, but you should just use Pandas or something. But basically, the Dask itself has an overhead, and has a scheduling overhead, and you want the partitions to be large enough such that the actual tasks you're executing are significantly larger than overhead. So today we'll actually inspect the metadata in your data set. We'll see how large your partitions are, and we'll also take into account any column selections that you're doing, and we'll automatically fuse any or combine any partitions to get sort of, meatier partitions, for lack of a better word, get them into a space where we know Dask actually will perform quite well. So you could do this before sort of manually, but this is now happening automatically on the fly for you. And then the last optimization I wanted to mention for the query planner is just basically getting rid of sort of unnecessary merges or unnecessary shuffles. So in this example here, we read in some data sets, we do a merge on one column with two of them, and then we do another merge here, and then we do some group by reduction. In a diagram, it looks sort of like this, and historically we would have 4 shuffles here. So we do 2 merges, one here, and each of the inputs we would have to do this like big expensive shuffle operation. So for example, for this shuffle, for this join here, we would shuffle both of these input data sets into it. That's an expensive operation. We would then shuffle for the next join, we would then shuffle this data set, and then we would shuffle this already shuffled, or already sorted data set. And the optimizer is now intelligent enough to realize I actually don't have to there's a redundant shuffle here before. So we can turn this computation that currently has 4 shuffles into one that has 3. So this is sort of a toy example, so going from 4 to 3 is nice, but it's not really a huge deal. But it's pretty common to have 5, 10, 15 merges that you might want to do in a query. So where you'll really see a big impact is going from a situation where you have 15 merges down to 5, something like that. Okay, so kind of summarizing here, because of pyro strings, because of P2P shuffling, because of our query optimizer, Dask is now a lot easier to use just out of the box. Before, Dask could be incredibly efficient, but you have to know sort of how Dask works under the hood. You have to do sort of, you have to customize things manually a lot. That's no longer the case. Now, a lot of these optimizations will happen automatically for you. It also scales better, and it also is a lot faster. Again, we're sort of encoding Dask best practices into some of these optimizations, so you're getting that sort of for free. This is useful for everyone, but in particular, new users who maybe don't know how Dask already works under the hood. They don't have to worry about that. Just to give a sense for the scale of these improvements. So in a minute, we're going to talk about benchmarks, and I'll say there's like a bunch of queries here. This is one of those queries. I think this is query 3. We see the legacy implementation here for this query. I think it took 950 seconds to run. This legacy implementation is just before, this is DataFrame 1.0, I guess. And then we can see what happens to the runtime as we add in these subsequent updates, where by the time we've included all 3 of our updates, we are now having a 20x improvement in the runtime. Again, this is like no change in user code. This is just, upgrade to the latest version of Dask, and your code is now 20x faster on half the hardware. Now, it's not always going to be 20x faster, right? It depends on the actual workflow, but this is pretty representative of what we do see in the wild. So this isn't like a 10 or 20% improvement. This is like order of magnitude or more improvement. Okay, so that's it for sort of the technical updates side. So let's go ahead and look at how this new and improved Dask data frame compares with other libraries in the space. So historically, when dealing with larger than memory, just like big data sets, tabular data sets in Python, the 2 tools that people tended to reach for were either Spark or Dask. And there's really good reasons to use either one of these libraries depending on your specific situation. More recently, the last 5 years or something like that, there have been some new projects that have come into the space, and in particular DuckDB and Polars, which have gotten a lot of traction, rightfully so. So the space is getting more fun and exciting. So let's see how Dask compares to these other tools. So what we did was we took all 4 of these query engines and plugged them into the TPCH benchmarks. For those who aren't familiar, TPCH benchmarks are sort of it's a set of basically database queries that you can run on synthetic data. It's sort of an industry standard that does a lot of the similar stuff I just showed. It loads in data sets, it does group bys, it does joins, it selects rows, does aggregations, sort of a lot of the standard, database query analytics stuff you would see. This is just going to give kind of a highlight or a high-level summary of some of the results. If you're interested in seeing more details, I recommend going to coiled.io/tpch. That has a sort of deeper dive into the methodology used for the benchmarks. So yeah, because the data is synthetic, we were able to run at a variety of scales. So we ran at 100 gigabytes, 1 terabyte, and 10 terabytes. That's the size of the data set. Again, I won't go too far into the methodology, but the one thing I do want to point out, because it's kind of a glaringly obvious thing, is that Dask and Spark are distributed engines, and DuckDB and Polars are sort of single node engines. So DuckDB and Polar were run on a single large VM, and Dask and Spark were run on clusters of many small machines. The one thing to keep in mind here is that the total number of cores and memory available to the libraries was the same. So if, I'll make up numbers, if Polar was run on a 32 core, 128 VM, we had the same number of cores and same amount of total memory for Dask and Spark, just spread across many machines. So let's look at the 100 gigabyte scale. Apologies in advance. This is this is not a great plot. It's really busy. If you're colorblind, I'm so sorry. They are at least in order as well, the different colors to indicate things. So what you're seeing here on the x-axis is this TBCH benchmark suite is composed of 22 different queries. That's what you're seeing on the x-axis, each individual query. The y-axis has the runtime for each query, and then obviously the different query engine we're using here. The main takeaway, I should say this is the 100 gigabyte scale. It was on 32 cores, and I didn't write it down. I think it's 128 gigabytes of memory. So not quite out of core, but right on the edge. 100 gigabyte data set, 128 gigabytes of memory available. So we were really happy with the Dask result here, the purple and leftmost color. It's basically on par with all of these other technologies. It's actually, in many cases, the sort of second fastest one. Again, Dask got a 20x improvement here. So if we were to make this plot, a year ago, it would have looked much worse for Dask. So we were happy to see that improvement. The other takeaway is DuckDB is really fast at this scale. So if you have data that's in the hundreds of gigabytes scale and you're comfortable with a SQL interface, and you really want to push performance, DuckDB is a great choice for you. Polars, so I should point out Polars does fail in a few cases here. It's kind of hard to see, but query I think 5, 7, 9, and 13. It's just we didn't include it in the plot. It timed out there. Polars does well on the simpler queries where you're really reducing the total amount of data that's going in the query. For the more complex queries where you might have a join or multiple joins and you don't really reduce the data volume, Polars tends to struggle a little bit there. I should also say that Polars is the newest of all of these query engines, and it's a very active project that's moving quickly. So I would expect these numbers to go, next SciPy, when we give the update to this, the Polars numbers, I imagine, will be much better. And then, the last one is PySpark, which also, it performs decently well to scale. This PySpark really shines at larger scale, so this is even kind of small for PySpark. So it does, in particular, okay at the, again, the simpler queries and the larger queries. It still completes and does reasonably well, but it does take a little longer for those. For the terabyte and 10 terabyte scale, Polars just did not perform well to scale, so things get complicated, I guess, is the main answer. So we're not going to include Polars in these plots, and for reasons that I'll mention in a minute, we're also going to start doing pairwise comparisons. So first what we do is we look at Dask and DuckDB here. Again, x-axis is all the different queries. We're now looking at the relative difference on the y-axis. So above 0 in purple, Dask was faster. Below 0 in blue, DuckDB was faster. And what we see here is it depends really on what you're wanting to do. Some queries Dask is faster, some queries DuckDB is faster. Again, the more simple queries is where DuckDB is really doing well, and then the more complex queries that don't really reduce the data volume is where Dask does well. If we then increase to the 10 terabyte scale, I should mention we're keeping the hardware the same here. So this is 128 CPUs, half a terabyte of memory. When we increase this and start going out of core, that's where Dask really starts outperforming DuckDB. So DuckDB can still do out of core, and actually some of the simple queries we were really impressed. DuckDB was not designed for like churning through 10 terabytes of data, and then for the simple queries, it's actually doing quite well. But what we like about this, what we were happy to see is that Dask is performing pretty consistently. We can do all of the queries. Some of the queries were slower than DuckDB, but DuckDB fails for some of the more complex ones. So Dask is a good, robust tool for this large data space. Now, last but not least, Dask versus Spark. So for 1 terabyte, what we see here is Dask is generally, so there are some queries where PySpark is faster than Dask, but Dask is actually is on par with Spark, if not a little bit faster. Again, PySpark actually just needs a lot of resources to, this isn't quite out of core yet, but as we turn up our scales, as we turn up our data volume, we see Dask really start to kind of outcompete PySpark a little bit. Went the wrong way. We actually, so in the Dask versus DuckDB chart, we kept the hardware the same. We here are increasing our hardware because PySpark just was churning for like hours and hours at that super out of core scale. So here we're increasing our data by a factor of 10 from 1 to 10 terabytes. We're also increasing all of the hardware by a factor of 10 as well. So here we have 10 terabytes of data and 5 terabytes of RAM. And what we see is basically PySpark starts failing for some of these queries. So you really have to throw a lot of hardware at PySpark for it to perform well at these scales. I mean, you don't want to, it's hard to process, or to process 10 terabytes of data, you would need, 50 terabytes of memory or something like that for PySpark. It starts becoming sort of absurd amounts of hardware to get things to be performant there. Okay, so main takeaways are DuckDB performs actually like surprisingly well at a lot of the scales we tested. It does start to struggle at the sort of 10 terabyte scale, really when things start becoming drastically out of core. In particular, that queries that don't reduce that data volume very much. But if you're not in that range and you are comfortable with the SQL interface, DuckDB is a really good choice these days. Spark works reasonably well at large scales, but you do have to throw a lot of resources at it. So you do have to provide lots and lots of hardware. So it can get pretty expensive. Dask is competitive now, which we were happy to see. It actually is on par. Again, at certain scales, DuckDB is a lot faster than Dask, but at the really large scale, Dask does become sort of a very good choice. We do see lots of room for improvement still. So what's next to come? So we do see, in particular at the larger dataset scales, we do see quite a bit of overhead in some of the queries in transferring the computation from your local Python session to the Dask cluster. So that's just literally generating and sending the graph to the scheduler for computation. It's up to 50% of the runtime in the worst case scenario. So half the time is spent just sending the graph, then the computation is the other half. The good news is we've identified 2 to 4 sort of hotspots, and we're hoping to resolve those pretty soon. The other is P2P shuffling also has a pretty significant overhead, so it's way better than the previous task-based shuffling algorithm. That said, it's not perfect. There's still room for improvement. There's a sort of flat 30 to 40% overhead, internal overhead in the shuffling operation. And then it's kind of hard to quantify this third one, but it's still early days for the query planner. So we've added a few sort of, I don't want to say simple, but like obvious low-hanging fruit optimizations for the query planner. But there's lots of room for improvement here. Really the important thing is like the low-hanging fruit has been plucked, I guess, and we have machinery now in place for adding more optimizations. So there's a lot of room for growth here. And then I also wanted to mention that a lot of the stuff I talked about today also applies to other parts of the Dask project. So this is focused entirely on Dask DataFrame for scaling pandas, but there's Dask arrays as well, which is for scaling NumPy, used pretty commonly in the geospatial space. And a lot of these same improvements are coming to Dask array as well. So the P2P shuffling algorithm I mentioned is going to be used in array rechunking. Array rechunking sort of inherits all the same problems that DataFrame shuffling does. And also the query optimizer coming to Dask array as well. So with that, I'll say, yeah, thank you all. And do you have questions?
All right, questions? Pass the mic over. Thanks.
Hi. So I'm not entirely sure on the connection between Dask, Pandas, and NumPy, but in this room, in the previous talk, the presenter was talking about the new string data type in NumPy 2.0, and he actually referenced about PyIO strings. So will you take advantage of that in future versions of Dask?
Good question. Unfortunately, I missed the talk. Apologies, Nathan, if you're in the room. Yeah, so I'm not sure.
Okay.
Other questions?
Thank you. My question is when you say that now, is it like the last half year, last year, or what's the baseline compared to? So if my team tried it like a year ago, is it improvement since then, or
great
it's
question? Yeah, definitely improvement since a year ago. It's a little complicated because like not all three of these features landed at the same time, or became like the default at the same time. So I would say the last, I should have the release number off the top of my head. I would say the last like 3 months, we've probably had all of these turned on by default. Yeah, hopefully that gets at the question. Yeah, follow up.
Sorry to follow up. And do you have a timescale when this will land for Dask arrays rather than a data frame?
Yeah, great question. So we are actively seeking user input. So the array chunking already exists. It's off by default. There's a toggle I can point you to, just a config option you switch, and then you can use the array rechunking. The query planner, as of last Friday, actually, we got a switch for that as well. You're going to have a bad time if you use it today. Don't turn the switch on, but we're getting there. So yeah, I don't have an exact answer, but like the next few months, I hope that's vague enough to cover my end and hopefully satisfying for you. Less than a year, more than half a year. I don't know. Yeah.
Additional questions?
So, question about the array, the Dask arrays part. Is the plan to sort of, are there similar techniques you can sort of apply to what you did for the data frames, and what are some of the biggest hurdles you see in terms of getting similar performance improvements?
Yeah, so I mean, luckily there's a pretty good mapping between the two. There's almost like a one-to-one mapping between array shuffling data frame shuffling and array rechunking. Big task graph, lots of memory blowing up. So, and again, that already exists in Dask today. It's just behind a feature flag. So, anyways, that work is like a great one-to-one mapping. The query optimizer is a little different. We have to basically just like how we rewrote Dask from the bottom up to take into account that query optimization. It's not going to be exactly the same because we do have some of like the core things that all the Dask collections will share in place, but we're going to have to write a lot of the like array domain specific stuff in this new expression language. So that, anyways, that's going to be the big lift on the development side.
Because I saw that you mentioned, so one of the pieces was the I/O portion, like you were sort of showing that graph. Do you think that'll be a challenge then for the array, since it's not necessarily the same where you're doing that I/O directly within the library?
Oh, you mean like you're using, I don't know, X-ray or something to open up a Azar data set?
Yeah.
Yeah. So, yeah, I don't know. I would have to talk with the X-ray developers to have a more informed answer for you. Yeah.
Thanks.
Yeah.
All right, let's thank James again.
Thanks.